Okay, I'm going to do the motion characteristics of oscillation follow-up. I'll just do sort of one of each type of calculation. So we're going from the position to the velocity here, the position graph to the velocity. So I'm going to pick a random point, maybe here, and to find the velocity, I need to find the slope of that, which means that I'm going to need to find the slope of the graph at that point, which means I want the tangent line to the graph at that point. So I'm going to use a ruler here and try to draw a line that has the same slope as that point does. Okay, so that seems to sort of kiss the curve right there. And then I want to find the slope of that line. That will be the velocity at this time, which looks to be, this is 6 seconds, this looks to be about 5.4 seconds. So I'm just going to take the endpoints here. This looks like it's about right there, and this one is right there. Actually, maybe I'll go right here since that crosses the nice 0.50 meters, and that looks to be about, there's 4 seconds, there's 4.5, so this looks like 4.8 seconds, we'll call it. So velocity is the slope of that line, which is the change in position, change in time. If we had taken 2 points on the curve, we would have found an average velocity. This is not, I'm not going to choose this point after all, actually, because it looks like I'm choosing a point on the curve. I don't want to give you that idea that I'm choosing a point on the curve. So I will take this point down at the bottom, which looks like it is at about 4.7 seconds. Okay, so the change in position, the final position here would be 0.65 meters minus, looks like it ended down at 4.94847, so about 47 centimeters. The final time was 5. Let's see, maybe 5.6 seconds, and the initial time was 4.7 seconds. And I get from that 0.2 meters per second, which is 20 centimeters per second. Now, knowing how to check this is really important as well. So this is the slope of the curve at 5.4 seconds. So what I'm going to do is go over to the graphs where we can check. So it was the first one. We're looking for 5.4 seconds. So there's 5.5. So we're maybe here. Come up on the graph and see where that is. Okay, so I go over here, and yeah, that's about 0.2 meters per second, which is just what it should be. So we're looking at the value here, not the slope. If we looked at the slope of this graph, that would give us the acceleration. Okay, now we're going from the velocity to the displacement, so we have to look at an interval. There's no such thing as finding the displacement for a point, because you need a time for time to pass. So I'm going to go from here, which is 1.7 seconds. I'll go from here to, let's say, I don't know. I'm trying to make a sort of a harder interval for you. I'll go maybe up to this maximum here at 1.85 seconds. So the area that I want is the area between the velocity graph and the t-axis. So the t-axis is here, the velocity graph is the curve, so it's this area that's negative and this area that's positive. So when the velocity is negative here, the displacement is negative, and it's positive here. So I should expect an overall positive displacement because I'm moving a lot further in the positive direction than I am in the negative direction. So I'm going to approximate this one as a triangle. I'll start with that one first. My delta x will be half the base times the height, and the base is this time interval. Looks like this occurs at about 1.75 seconds. So that time interval there is 0.05 seconds. And this goes to, it looks like negative 0.35 meters per second. So I do the product there, and I get negative 0.00875 meters. So that's negative 8.75 millimeters. Okay, so that's part of it. If I'm going to look at this part, I'm going to call this, let's see, triangle would cut off some stuff. I'm going to call it like a trapezoid. I'm going to go maybe a little bit up here. I'm going to flatten this off. So that's going to be my approximation. So I'm going to take that down. It looks like this time is like 1.82 seconds. So my trapezoid looks like this. If you go for a triangle, you're going to cut off quite a bit. So I think I'll be a little bit high on here, but closer than if I had cut off all that. So this part is 0.03 seconds, because it ended at 1.85, it began at 1.82. And this whole thing here goes from, we said that was 1.75, so it's 0.1 seconds wide. And the max V appears right at about 0.5 meters per second. So that's the area I want. And I need half times my height here times the average of my bases, or sorry, the half gives you the average, so the sum of the bases here. Okay. And that will give me 0.0325 meters, or 32.5 millimeters. So the total delta x is going to be negative 0.02375 meters, or negative 2.38 centimeters, something like that. I'm sorry, positive. So the positive one was bigger. Okay, so now we need to check that, and we can go to the position graph. So we're looking at the third position graph. We started at 1.75 seconds, which is here. So it actually started at 1.7 seconds, which is a little earlier. We started like here. And we ended at 1.85 seconds, which is here. So we're about at the maximum speed. So we're looking for the displacement, and that is this. That is the change in position. So our initial position, it looks like, was 0.515 meters. And our final position was, looks like it's about 0.54 meters. So we look at the difference between the two, and we get 0.025 meters, or 2.5 centimeters, and our prediction was 2.38 centimeters. So that's pretty darn good. Pretty good, especially for sort of approximating those curves. So that's the deal. The area on the velocity graphs gives us this sort of vertical change on the graph for that same time interval. All right, there you go. You have, as long as you know how to check them, you have sort of as much practice here as you want and need. All right.